This video will give examples with exponential functions. Sketch a graph of y equals 3 times 2 to the x and a graph of y equals 3 times 1/2 to the x. So we'll just draw these all on the same graph. Our first one, we know that both of them have an a equals 3. So when we plug in x equals 0, what we end up with is 3 times 2 to the 0, or 3 times 1/2 to the 0, and in either case we end up with just 3. So we can draw a point here. Now, our first graph, y equals 3 times 2 to the x, will show an exponential increase by 2 each time, so that when x equals 1, we have y equals 6. And when x equals -1, we have 3 over 2, or about 1.5. So we can draw our exponential graph something like this. Now, what about y equals 3 times 1/2 to the x? It's the exact same thing, except the opposite. So when x equals 1, we have y equals 1.5, and when x equals -1, we have y equals 6. And we can see that these two graphs are exactly symmetrical. And if we think about it, this makes sense because essentially our blue graph here is equal to 3 times 2 to the power of -x by the rules of exponents. And so when you have the exact same function except one of them with an x and the other with a -x, you end up with two functions that are symmetrical over the y-axis. Find an exponential function that passes through the points 2, 243, and 427. So we'll start out with our formula for exponential functions. Y equals a times b to the x. And I'll just plug in our numbers into these functions to see what we get. So I'll say 243 equals a times b to the power of 2, and 27 equals a times b to the power of 4. Now we can divide these equations by each other so that we end up with 243 over 27, which is 9, and that equals a times b squared over a times b to the 4th. Our a's cancel, and we end up with 1 over b squared. So that tells us that 1 over 9 equals b squared, or b equals 1/3. Now we can plug this into our original equation. So we can say 243 equals a times 1/3 squared, or 1/9 times a, and that means that a equals 243 times 9. So we have as our final equation y equals 2,187 times 1/3 to the power of x. Solve 1/2 to the power of n minus 1 equals 16. So first thing we can do is we can expand our exponent so that we have 1 to the power of n minus 1 over 2 to the power of n minus 1, or 1 over 2 to the n minus 1, equals 16. Now we can recognize that 16 is equal to 2 to the 4th, so we can write that in. And now what we can do is some algebraic manipulation so that we end up with 1 over 2 to the 4th is equal to 2 to the power of n minus 1. And now 1 over 2 to the 4th, we can rewrite this expression as 2 to the power of -4 by our laws of exponents. And now we can see that -4 equals n minus 1. So n equals -3 is our answer. Solve 5 to the 2n plus 1 is greater than 125 to the 3n minus 4. So first thing we can do is recognize that 125 is equal to 5 cubed. So we'll replace 125 with 5 to the power of 3. And now we can use our properties of exponents and rewrite this as 5 to the power of 9n minus 12. And so we can see easily that 2n plus 1 must be greater than 9n minus 12. And so now we can just solve for n by subtracting 2n from both sides. And we end up with 13 is greater than 7n, or n is less than 13 over 7. So far in all of our examples, we've only been looking at cases where the base, or this number right here, is greater than 1. But in cases where a base is less than 1, some things we have to be more careful about. So looking at this inequality, we might be tempted to say that the answer is simply n is greater than 4. But let's consider this carefully. If we look at the graph of 1/5 to the power of n, it looks something like this. And so 1/5 to the power of 4 is somewhere around here. And if we were to say that n is greater than 4, well, we see that the graph is actually decreasing at this point. And in fact, what our answer should be is n is less than 4. So the reason this happens is because when we try to solve our inequality, what we do is we rewrite 1/5 to the power of n as 5 to the power of -n. And so on both sides we have 5 to the power of -n is greater than 5 to the -4th, which means that -n is greater than -4. And now, when you try to solve for n, remember that when you multiply or divide by a negative with inequalities, you have to flip the sign of the inequality. And so that's why you end up with n is less than 4 as opposed to n is greater than 4. So this is something to keep in mind whenever your base is less than 1.